We're looking at the projection of vectors, or the projection of one vector onto another vector or in the direction of the other vector. And we're also looking at vector dot or scalar products, which are used in the mathematics of projection of vectors. There are two vectors, v and u, and when we talk about projecting v onto u, we mean how much of v is in the direction of u. Before we look further into this idea, I want to recap some of the vector ideas we've covered previously. We've looked at vector addition, where if you're going from A to B and B to C, that's the same as going from A to C, or two forces applied on an object, force A and force B, produce the same effect as force C applied on that object. So we've also looked at expressing a vector as the sum of the components. So the vector u here can be split up to its component in the x direction and its component in the y direction. The length of the vector on the page is the magnitude of u, and so we can use trigonometry to express x in the component in the x direction, y the component in the y direction. And we use this unit vectors I and j so that we express u as x times the unit vector I plus y times the unit vector j. And you've worked before with expressing a vector v into its components in the direction of the x-axis and in the direction of the y-axis. And we look at it again here because projecting one vector onto another vector is very similar to the way we break a vector into its components in the x and y direction. Coming back to our vectors u and v, and I can drop a line down here, which is at right angles perpendicular to u, and I can express v as a component in the direction of u and as a component at right angles to u. And if this is the angle theta between them, then I could use trigonometry to look at the size of this vector, the magnitude of v times cos theta, and this vector, the magnitude of v times sine theta. And looking at that algebraically, I can express v as its components parallel and perpendicular to u. I can say that the vector v equals v cos theta times a unit vector in the direction of u, v cos theta, plus v sine theta in a direction. And I'll just put this little symbol here to use a vector perpendicular to u. So just looking at the component of v that's in the direction of u, the projection of v in the direction of u equals v cos theta times a unit vector in the direction of u. And we can compare that to the formula here for the projection of v in the direction of u. And this formula looks a lot more complicated. It's got a dot product in there, and the dot product is defined here as the magnitude of u times the magnitude of v times cos theta, where theta is the angle between them. So we've got a u dot v, we've got the vector u instead of the unit vector u, and then we've got this u squared down in the denominator. So let's have a look how these two formulas line up. So I'm going to express this formula as v times the magnitude of u times cos theta. So I've multiplied by the magnitude of u. You can see now that gives me that definition of the scalar or dot product. And then I need to times that by 1 on u, because I've multiplied by u. I also need to times it by u hat. And instead of u hat, I'll also write 1 on u times u, which is the same as u hat. So there's the expression. You could stop the recording if you like and just check that that expression is the same as the expression above for the component in the direction of u. And at this stage, we're just focusing on that component in the direction of u. So bringing those like terms together, we've got, and expressing this as u dot v as defined above, u dot v times, or u dot v divided by the magnitude of u all squared times the vector u. And notice that u dot v is not a vector quantity, that's a scalar quantity that goes into calculating the magnitude, and divided by v squared. If we come up here, that has the same effect as using the v cos theta times a unit vector in the direction of u. And you might be thinking, well, why do we make this projection formula so complicated, and why do we bother with u dot v? And the answer lies here in the scalar product being expressed either in component form or in the cos theta form. And whichever way you express it, so the component form means if you know the components of v and u, and I've given some examples here, and we'll look at that in a second, where v is 2 in the x direction and 4 in the y direction. If you know the components, you can calculate the dot product from the components directly, and then you can use this formula in the same way as you would if you use the cosine version to produce the projection of v onto u. So we'll calculate the dot products and the projection of v onto u based on the example vectors that are shown here for v and u. But before that, let's look at why we care about the projection of one vector onto another and the calculation of the dot products that go into that projection.
For decades, NASA has stolen gravity from neighboring planets and used it as fuel for deep space exploration. It's called a gravity assist. And because of it, we've been able to travel to regions outside the solar system that would otherwise be unthinkable. So how does it work? In a nutshell, a gravity assist is a technique that changes the spacecraft's velocity relative to the sun by swinging through the gravitational field of a planet or moon. To accelerate, the spacecraft flies with the movement of the planet, picking up a small chunk of its orbital energy in the process. To decelerate, the spacecraft flies against the planet's motion. The larger the planet, the stronger the gravitational power. Meaning the spacecraft gets a bigger push or pull, all on the dime of the planet's gravity gas card. The first flyby technique can be traced back to the Voyager missions of 1977. At the time, the 2 unmanned spacecraft were launched into space to study the gas giants, Jupiter, Saturn, Neptune, and Uranus. But the distance to Jupiter is deceptively long, only about halfway to Saturn. And the vehicles the probes were launched aboard, the Titan III Centaurs, could only provide enough energy to get them to Jupiter. The launches, of course, were planned so that Jupiter aligned perfectly with the spacecraft's route. The orbital designers targeted the closest approach distance to achieve the desired speed. Afterwards, the probe's momentum pulled them away from the planet.
Gravity assist and aligning starships with a planet's gravitational pull so that you get that thrust. One reason that we care about projection of vectors. So let's just look at that dot product in component form. We've got V equals 2, 4, and U equals 5, 3, and U dot V, the dot product, the scalar dot product, is x1, x2 plus y1, y2, so it's 5 times 2 plus 3 times 4 equals 10 plus 12, 22. Now, u squared, the magnitude of u squared from the component form is 5 squared plus 3 squared, 25 plus 9 equals 34. And so we now write the projection of V in the direction of U equals U dot V on U squared times U dot V 22 divided by, I should say, not times, 34, and U is the vector 5, 3. Putting that in the calculator, 3.2 and 1.9, rounding to 1 decimal place. And if we come back to our diagram, 3.2 and 1.9 is just about here. So there's the projection of V in the direction of U. So we've used trig to look at the projection of V onto U. We've compared it to the formula which uses the dot product. And we've looked at the calculation of the dot product by giving an example where we've used the component form of V and U. And it's worth looking at the dot product calculated in the cosine form, and we can do that if you look at U and V. If we've got the component form, so we could calculate this angle that V makes with the x-axis and call that alpha. We could calculate the angle that, I should say that U makes. I could calculate the angle that V makes with the x-axis, and we could call that beta. And then theta, the angle that we would use in the dot product, is just beta minus alpha. Of course, we could also have used the cosine rule where we know V and U. We could calculate V minus U in component form and use the cosine rule to get theta. But let's use the alpha beta approach and just show that calculating the dot product for those two vectors gives 22 based on the cosine form. So we've got tan of beta equals 4 on 2. 4 on 2. We've got tan of alpha equals 3 on 5. 3 on 5. And we can use inverse tan to calculate beta and alpha. And using a calculator, beta equals 61.4 and alpha equals 31.0, and that's in degrees. So theta, which is beta minus alpha, equals 61.4 minus 31. Theta equals 30.4 degrees. So using the cosine approach for U dot V equals the magnitude of U, which is the square root of 5 squared plus 3 squared, 25 and 9 is 34, times the square root of or the magnitude of v, which is the square root of 16 and 4, square root of 20, times the cosine, I might fit it in here, cosine of 30.4 degrees. And putting that in the calculator gives us the same as the component form as we expect. The dot product u dot v is 22. To show that the scalar product or the dot product in cosine form is the same as the dot product in component form for any vector v and u, I'm going to use the cosine rule. And I'm going to create a triangle by joining u and v, the heads of u and v, to create a displacement vector here, v minus u. And with the cosine rule, I can get a relationship between this distance, which is the magnitude of v minus u, and these distances, the magnitudes of v and u, and cosine of theta, the angle between them. So let's do that. We've got, in general terms, v equals, we'll call that x2, y2, and we'll call u x1, y1, so that v minus u equals x2 minus x1, y2 minus y1. And then using the cosine rule, we can write the relationship, the length here, the magnitude of v minus u squared equals v squared plus u squared minus 2v u cos theta. So using the cosine rule, I'm looking at that triangle and relating the sides. Now you can already see in here, uv cos theta, we can see the scalar or dot product of u and v. So let's rearrange that where we make the dot product the subject, u dot v. The right-hand side becomes, because of that 2, we'll put a half out the front, and we've got v squared plus magnitude of u squared minus the magnitude of v minus u squared. So you might want to pause and just check that algebra. Now I'm going to use the component forms to express each of these magnitudes or squares of magnitudes in component xy form. So we've got, and then we'll simplify the algebra and we'll show the equivalence of our dot product. So v squared is x1, x2 squared plus y2 squared. U squared is x1 squared plus y1 squared, and then minus the magnitude of v minus u all squared is x2 minus x1 squared, put that in brackets, plus y2 minus y1 all squared. So you can probably see the x2s and the x1s squareds are going to cancel out, leaving us with just those cross terms, x1, x2, y1, y2, which is the component form up here. Let's have a look at that. And to see that, I'm just going to expand this expression here, x2 squared plus x1 squared minus 2x1 x2 plus y2 squared plus y1 squared minus 2 y1 y2. And we're subtracting that from this part, and you can see that all of those terms cancel out, leaving us with half times, and this is minus or minus, 2x1, x2, plus 2y1, y2, which gives us the component form of the dot product, x1, x2, plus y1, y2. So let's just go over what we've done. We've used the cosine rule to equate the sides and the angle of this triangle formed by VU and V minus U. We've used that to give us an equation which includes the dot product in the cosine form and equates that to the magnitude of the VU and V minus U vectors. We can use the component form to express those magnitudes. So now we've got an equation where we've got the dot product on the left side and the component form on the right side, which expands and simplifies to give us x1, x2 plus y1, y2.